Hello everyone, this is Mr. Navarrete again, and today we'll be going over periodicity homework number 2. So, without further ado, let's get started. Question number 1 asks us to define atomic radii. Well, just like in our geometry classes, we draw a quick circle. Our radius is from the center of the circle all the way to the furthest edge. So, using that as a base, we can say that our atomic radius is simply a measurement of the distance from the nucleus to the furthest shell. And in general, the atomic radii just tells us the size of the atom. Let's move on to question 2. For question 2, we need to define electronegativity. And in simple terms, electronegativity is an atom's tendency to attract an electron towards it. Factors such as size and the number of protons that are present in the nucleus help determine an atom's electronegativity. Awesome. Now we're going to move on to question 3. For question 3, we need to define ionization energy. And again, we're going to put it in very simple terms. Ionization energy is the amount of energy needed to remove an electron from an atom in its gaseous state. So not just from a solid or from a liquid, we're talking about when it's in a gas. So again, ionization energy is just the amount of energy needed to remove an electron from an atom in its gaseous state. And again, size will play a big role. For our last definition, we need to define electron affinity. And very simply put again, it's just the change in energy when an electron is added to a neutral atom. So you can kind of think about electron affinity as the opposite of ionization energy. Now that we have our definitions, let's look at these patterns on the periodic table itself. So for 5, we need to draw a simple periodic table and show the trends of atomic radius. Mine is a little bit different than yours. Just kind of make yours look like mine. The main point is just adding the trends. So as we go down a group, our atomic radius increases. It's so hard to write sideways. All right. And as we move across a period, our size decreases. Why does this happen? Well, as we move down, we have more shells of electrons, making it bigger. And as we move across the period, well, there are more positive charges in the nucleus. So it's pulling all of those electrons closer to them. Let's draw our next trend. So let's draw electronegativity. Now for this one, as we move down a group, our electronegativity decreases. As we move across a group, our electronegativity increases. Why do we see this trend? Well, remember, electronegativity is pulling an electron. So as we get bigger, it's harder for that positive charge to go reach out and pull another electron. However, as our atoms get smaller, it's easier for that charge to go out and reach another electron. Let's look at our next trend. So now we have to draw ionization energy. And this one, as instead of moving down, we're going to move up the group. Our ionization energy increases. I'm not going to write sideways anymore. Increases. That says increases. And as we move across a period, our ionization energy increases as well. Why do we see this trend? Well, as our atoms get smaller, the electrons are closer, they're held tighter. So it makes it really difficult for an atom to lose an electron to another atom. Now let's move on to our last trend. For our last trend, we need to show electron affinity. So in this case, as we move up a group, our electron affinity increases, as well as when we go across a period, it also increases. These are all of our trends. Let's move on to our next question. For question 9, it asks, why does a cation get smaller after it loses an electron? Well, I'm going to use hydrogen as an example. Hydrogen has 1 proton, and it also has 1 electron. I'm going to draw that there. Give it a different color, just so that we know which one is which. And our definition for atomic radius is, this would be its atomic radius, how far it is to that electron. If it loses an electron, then its new radius would just be from the center, just what the proton is. And that's what causes our cations to be smaller. But by losing an electron, they can pull the other electrons tighter. That brings those electrons closer. And in return, making our radius smaller. Let's move on to the next page. Well, if cations get smaller, why does an anion get bigger? Something to think about is magnets. And when you put them together, when they're both on the same side, they kind of push away from each other. And that's the same thing that happens with atoms and their electrons. So let me bring back my hydrogen atom. But now this time, I'm going to draw another electron. Now it's a hydrogen anion, and these two negative charges are going to want to be as far away from each other as possible. They're going to repel each other. But because there's this positive charge in the center pulling both of them, they're still going to stay close. So they're going to be as far away as possible, but still close to each other. So as I add more and more electrons, I have to add more and more shells because they're all going to want to be as far away as possible. So as a result, as we add more electrons, they repel each other. Further, we add more shells, and in return, this causes our atomic radius to be bigger. For question 11, it asks, why are alkali metals so reactive? Well, on the topic of shells, there's this cool little thing called valence electrons. Valence electrons. And what that means, it's just the number of electrons an atom has in the most outer shell. With valence electrons, they all follow this thing called the octet rule, which states that all atoms want to have 8 valence electrons in their last shell. So when we're looking at the alkali metals, all of the alkali metals have 1 valence electron. And because when an atom loses an electron, it loses a shell, it will have a full shell once it loses that electron. So our alkali metals are so reactive because it's easier for them to lose an electron. Not just any electron, a valence electron. To complete their octet. We're going to carry on these rules of the octet rule onto our next couple of questions. So for question 12, it says, why are all the noble gases so unreactive? Well, all of the noble gases have 8 valence electrons. Meaning that they already have a full octet. They don't need to go react with something else to fill and get more valence electrons. They already have them. So because they already have a full octet, they don't react with a lot of things. The last one that we're going to use the octet rule for now is for number 13. It asks, why do group 17 elements only gain 1 electron? So for group 17, all of them have 7 valence electrons. So they only need one more valence electron to fill their octet. Let's put our trends into practice. So for this question, it asks which one is larger. And looking back at my periodic table, I see that as I go down, I get bigger. And as I go across, I get smaller. So in this case, sodium and potassium, let me find them. Sodium, potassium. In this case, potassium is lower than sodium, so potassium is bigger. Moving on to the next one, helium and neon. Well, helium is here, neon is here. I know that as I go down, that means it's bigger. So neon is bigger. For this one, it has B versus C. So looking at our chart, B is here, C is here. As we move this way, we get smaller. So for this case, B is our larger one. Let's move on to our next one. Cl and fluorine. So Cl is here, fluorine is there. As we move down, we get bigger. So Cl will be our bigger one. Now we have bromine versus iodine. Same group, bromine and iodine. So as we move down, we get bigger. So iodine would be our larger one. And on to our next one, sodium and magnesium. So looking at our trends, as we move across, we get smaller. So sodium is our bigger one. On to the next one. We have argon and potassium. So while they are kind of across from each other, here argon, we can see that it's going to be one of the smallest ones, and potassium is going to be the bigger one going down. So potassium would be our bigger one, just because it's in one period down. All right, let's move on to our next one. Lithium and neon. Lithium and neon. So they're on the same period, but as we can tell on our trend, as we move across, we get smaller. So lithium would be our bigger one. Number 15 asks, circle the species that is larger, sodium or the sodium cation. And looking back at our notes, we know that if it's a cation, it lost an electron. So that means it's smaller because it lost a shell. So in this case, the normal sodium ion will be larger than the sodium cation. Let's try our next one. We have fluorine and a fluorine anion. And we know that when an atom gains an electron, it gets bigger because it needs more space for the electrons to repel each other. So in this case, our fluorine anion is going to be the larger one. For our next problem, we have our oxygen anion and our fluorine anion. And here, if we see, oxygen gained 2 electrons, and fluorine gained 1 electron. Here we can follow the same trend, gained more electrons so that it needs more space to repel. So O2 would be the larger one. All right, let's move. For our next one, we have the sodium cation and a fluorine anion. And this one is a pretty interesting one because they're both going to have 10 electrons, where we can kind of see which one's going to be bigger is by the number of protons. Now, sodium is going to have 11 protons, and fluorine is going to have 9 protons. So in this case, we're going to have more protons than electrons with sodium, meaning they're going to be able to hold tighter those electrons, versus fluorine which is going to have more electrons than protons, meaning that they're going to be pushed further away. So which one is larger? Fluorine. Might take some time to kind of wrap your head around it, but again, drawing these and seeing the models would help a lot. All right, let's move on to our next one. Here we have the magnesium neutral atom with the magnesium cation. So we're just going to follow that trend where because the cation did lose electrons, it did lose its shell. The protons are able to have a better grip. So magnesium is going to be the larger atom, the neutral version. Let's move on to our next one. So here we have a fluorine ion and an iodine ion. Which in these is going to be larger? Well, fluorine is only in period 2 versus iodine, which is way below it. So that means it's going to have more shells. It's going to have more electrons. So in this case, just based on shells, iodine is going to be bigger. Let's move on to our next one. Now we have aluminum and the aluminum ion. So same pattern. Because it did lose those 3 electrons, it did lose its outside shell, meaning that it is smaller. Protons are also going to be able to pull those remaining electrons closer. So aluminum is our larger one. Move on to our next one. Here we have chlorine ion. Here we have a chlorine ion and our fluorine ion. So just based on where they are on the periodic table, chlorine is below fluorine, meaning it has more shells. It's going to have more protons, more electrons, just going to be a bigger atom on its own. So chlorine is going to be bigger. Now we want to circle the one that has the largest ionization energy. So again, looking at our trends for ionization energy, as we move up, our energy increases. And as we move across, it also increases. So let's look at sodium and potassium. So sodium is here, potassium. So we can see that sodium is above potassium. Therefore, it's going to have a higher ionization energy. For our next one, we're going to focus on fluorine and bromine. Well, fluorine is here, bromine is here. So that means as we move up, it increases. So fluorine is going to have the larger ionization energy. So on to our next one. Now we have boron and carbon. So as we move across, our ionization energy increases. So carbon is further to the right. So that one is going to have carbon is going to have our larger ionization energy. Move on to our next one. Here we have chlorine and argon. So chlorine and argon. So which one's going to have the higher ionization energy? Argon is closer to the right. So argon is going to have the larger ionization energy. All right, our next one. For our next one, we have bromine and iodine. So again, as we move up, we're going to have a larger ionization energy. So in this case, bromine is on top. So bromine is going to have the higher ionization energy. Let's move on to our next one. Here we have sodium and magnesium. Sodium and magnesium. Magnesium is the one closer to the right. So magnesium is going to have the higher ionization energy. All right, let's move on to our next one. For our next one, we have argon and potassium. So argon is here. Next one, we have argon and potassium. So as we go up and we move to the right, it increases. So argon has the larger ionization energy. All right, let's move on to our next one. For our last one, we have lithium and neon. Lithium is here, neon is there. Looking at my trend, as I move to the right, my ionization energy increases. So neon is furthest to the right. Neon has a larger ionization energy. Now we're going to work on electronegativity. So if we remember, if we look at our trends, as we go down our periodic table, our electronegativity decreases. As we go across a period, our electronegativity increases. So now here we have sodium and potassium. Sodium and potassium. So potassium is lower. That means that the one with the larger electronegativity is sodium. For our next one, we want to see fluorine and bromine. So let's find them on the periodic table. Fluorine is here. Bromine is here. So bromine is below fluorine, so it has a lower electronegativity. So that means fluorine has a larger electronegativity. Let's move on to the next one. Boron and carbon. So boron is here, carbon is here. So as we move to the right, it increases, meaning that carbon has a larger electronegativity. Let's move on to our next one. Here we have chlorine and argon. Now this is where things get a little bit interesting. Argon is part of the noble gases, meaning that it's not going to want to go out and search for another electron. It's already happy. So chlorine is the one that's going to have the larger electronegativity, mainly because it still needs to complete its octet. So argon is already happy. It's not going to go out searching for something. Let's move on to our next one. Bromine and iodine. So here we have bromine, iodine. Iodine is lower than bromine, meaning that's going to have a smaller electronegativity. So that means bromine is our larger one. Moving on to our next one. Sodium and magnesium. So let's find them. Sodium. For our next one, we want to find sodium and magnesium. Our trend says that as we move to the right, we increase. So that means magnesium has a larger electronegativity. On to the next one. For our next one, we have argon and potassium. So argon is here, potassium is here. Remember that argon is a noble gas, so it's not going to want to hunt for another electron. So in this case, potassium is our winner for larger electronegativity. Move on to our next one. Lithium and neon. Here we have lithium and neon. And even though neon is all the way to the right, it's still not going to have an electronegativity since it has a full octet. So in this case, lithium has a larger electronegativity. And that was our last one. So thank you guys for stopping by. Hopefully that was helpful. And I'll catch you guys on the next one. Stay safe.